All right, this is covering sections 3.1 and 3.2, looking at exponential and logarithmic functions. So starting out here with exponential functions, so we're looking at something that's of the form f of x or y equals a to the x, where a is the base and x is a real number such that a is greater than 0 and a is not equal to 1. It says we do not allow 1 as a base of an exponential function. If a is 1, the function becomes a constant, which would be f of x equals 1, which is not an exponential function. So for these first couple, we're just going to evaluate, basically figure out what each of these values is equal to for the exponential function 2 to the x. So we're just going to plug in the number into the x and see what we get. If we simplify it using maybe even some of our exponent rules or, just plugging it into the calculator. So for this first one, this is going to be 2 to the negative 1, which we know that we can make exponents positive by moving them to the opposite side of the fraction. So this would be moving this one to the denominator. So that would be 2 to the first goes to the denominator. 2 to the first is just 2. So this reduces to 1/2. For b, 2 to the third, basically that just means 2 times 2 times 2, which is 8. Right. Letter C, this one would be, because it's a decimal there, something you're going to have to put in your calculator. Just do 2 raised to that power and give an approximate answer here. And it comes out to be 30.27. Now the trickiest one of the bunch here is letter D. This is going to be 2 to the 5/2. So here we're going to have to use a couple of our exponent rules. So first thing I'm going to kind of use is like the power rule in reverse. I'm going to separate this into 2 to the 5th raised to the 1/2. So I just separated that 5/2 into 2 to the 5th and then to the 1/2. So then that gives me 2 to the 5th is 32. And then that's 32 to the 1/2, which, remember when we did way back at the beginning of changing something from radical form to rational exponents, the index of the radical is the denominator, the exponent is the numerator. So this would be 2 for the index and then 1 for the exponent. A 2 of an index just basically means square root. So we're looking at the square root of 32, which we could then come over here and we could break down 32 doing a factor tree. And we see we have a pair of 2's and another pair of 2's. So for each pair, 1 comes out. And then we had a 2 at the end of a branch that did not get circled, so it would stay underneath. So this would end up giving us 4 square root of 2. All right, so that was just practicing some of those, evaluating different exponential functions using some of our exponent rules. All right, next we're going to look at graphing just a basic exponential function, just f of x equals 2 to the x. Couple of things, and I'll highlight here from this little statement that you've got. It says when graphing exponential functions, you will need to find the horizontal asymptote. For most functions, right, the horizontal asymptote will be the equation y equals 0 unless there is a vertical shift, meaning something that is added or subtracted to the base after the function. All right, so it says for most of them, it's going to be y equals 0, right, unless you have something that is added or subtracted to that function. So what they mean by that, it would look something like this. It would be like y equals 2 to the x and then like plus 3. So that plus 3 there would make that vertical shift happen, which would make that have a different horizontal asymptote opposed to just y equals 0. Okay, in our first one here, we're just looking at your basic one, just y equals 2 to the x, which is just going to have a horizontal asymptote of y equals 0. There's no vertical shift there. There's nothing that's been added to it. And we're going to fill in our table here so that we can get some points to graph it, and then we'll look at domain and range as well. All right, so horizontal asymptote is y equals 0, which is actually just the x-axis. So I'm going to put a dotted line here, right, and this represents that horizontal asymptote of y equals 0. All right, now to figure out each of these values, we're plugging in, kind of like we did in that first example, we're plugging in each of these x's into the function and seeing what we get. So this is going to be 2 to the negative 3, which becomes 1 over 2 to the third. 1 over 2 to the third is 1/8. 2 to the negative 2, that becomes 1 over 2 squared, which is 1/4. 2 to the negative 1 is 1 over 2, or a half. 2 to the 0, anything to the 0 power is equal to 1. 2 to the first is just 2. 2 squared is 4. And 2 to the third is 8. So now we have all those x values and y values, and we can plot this function. All right, so some of these are really small, so we're just going to have to do a little bit of approximating here. So we have negative 3 and 1/8. We'll say by maybe about right there. Negative 2 and 1/4, just a little bit higher. 1/2. 1. 1, 2. 2, 4. And then 3, 8. And we'll connect those together. And we get that basic exponential function. Okay, now that we've got it graphed, let's talk about the domain. So domain, we're talking about x values from left to right. X values from left to right. I see there that on the left-hand side it has an arrow that's pointing to the left. So that must mean it's continuous and it keeps going that direction. So that's towards negative infinity. And then on the right-hand side, you can see that arrow is, or that curve is kind of pushing out to the right and keep going that way. So that means that that's going towards infinity. Now the range here is going to be the part that's a little bit different because it's got that horizontal asymptote, right? That does not go past that line there. So it is, if you start from the range doing y values from bottom to top, all right, we do not start that function until we're basically on the other side of 0. So we're going to start at 0, all right, and we're going to use a parenthesis because it's not equal to 0. And then it keeps going up, so that means it's going towards infinity. So it gets really close to 0 down there at the bottom, but it doesn't actually cross it, so it starts at 0 and goes to infinity. All right, so that's just your basics of a exponential function and how you can graph it. So you have a table of values and then just plot those points. All right, the next little bit is going to be focused on exponential word problems. All right, starting out with compound interest and continuous interest. So here, compound interest formula, you can see A equals P, 1 plus R over N to the NT, right? And it shows you there what each variable stands for. And then it also gives you that possible values for N. So these are words you would see in the problem and you'd be looking for, that would tell you how many times it is compounded within a year. And that would be the number that you would want to use for your N value. Key things to look for in the problem are the words compounded, and then it's one of these N values or words that come there for the N. That would be the keys that would tell you that this is the formula that you want to use. So if we freed our first one here, suppose $2,500 is deposited into an account paying 6% interest per year, compounded semi-annually. So right there, that's the key, that compounded semi-annually, that tells me that this is the formula that I wanted to use. It says to find the amount in the account after 10 years with no withdrawals. All right, so let's see. We need to figure out where each of these things go. So A, it says the amount after T years, which I think is what we're actually trying to find in this case. P is the principal, so that's what you're starting with, which I believe is $2,500 in this case. Our interest rate here is going to be 6%, but the key thing is this must be a decimal. So if it is given to you as a percent, as it is here, you must change it to a decimal before you can use it in your equation. So if I take 6% and I want to change it to a decimal, currently the decimal is behind the 6, so I'm going to move it 2 places to the left. So 1, 2, and I'm going to put a 0 in that place. So this tells me that R is 0.06, and that's what I'm going to use in my formula. It says compounded semi-annually, so looking here at this list of possible values, this tells me that N is going to be equal to 2, and we are trying to figure out how much is going to be in that account after 10 years, and that is going to be our T. So let's plug all this information in. So we're trying to figure out A. We've got $2,500. 1 plus 0.06 divided by 2, because that's our N, raised to the 2 times 10. So 2 being N, 10 being T. So let's simplify this down. All right, I'm going to do 0.6 divided by 2 and get 0.3. And then 2 times 10 is 20. And we'll add 1 plus 0.03. And then this would be a point where I feel like you should be able to type this into your calculator, exactly like you see it there, with the 2,500 parentheses 1.03, and then raise it to the 20th power. And since we're talking about money, I'm going to put my $sign, and I'm going to round it to 2 decimals. And when I plugged it in, I got $4,115.28. All right, so just knowing where to plug those values in and getting them plugged in, pretty much from there, it's going to be plug it in the calculator and see what you get. Okay, the other way that we can compound money with an exponential is through continuous compounding. And here the key is going to be, you're looking for that word continuous. All right, if it says continuous anywhere within that problem, you're looking to use this A equals P e to the RT. Right, the variables mean the same things as they did in the previous formula. The key thing here, though, is this statement here. It says that note E is not a real number, or is a real number, not a variable. The value of E is approximately this. So we're not using E as a variable here. E is a number. It's an irrational number. It's a similar type of example. This time, still got that $2,500, still doing 6%, but that key there is that it says compounded continuously. Compounded continuously tells me that I want to use this, some people refer to it as the PERT formula, P e to the RT. And we're still doing 10 years, but there is a little slight difference here. It says how much interest was earned, right? So how much interest is earned. So we're going to start it out the same way, kind of like we did the last one. Plug it in and see what we get. There's going to be a slight little difference to it once we get to the end. So we're still starting with $2,500. We've got E 0.06 times 10. 2,500. E 0.06 times 10 is going to be 0.6. At that point, we should be able to plug that in the calculator. Right? And E is a function you'll see on your calculator. Right? You have to hit the second, and then there's a button that has an LN on it. Right? And second is an LN, and you would see that E. And when you plug that in, we get $4,555.30. Now the key thing here is that it says how much interest was earned. So this is how much money is in that account, but we only want to know the interest. So what we have to do here is we take what we just got, and we want to subtract out the principal, what we initially invested into this account. Right? So when we do that, we're going to get that over this 10-year period, they have gotten $2,055 and 30% interest in that account. So anytime they ask you for just the interest, right, you're going to subtract out that initial amount that you had deposited or invested in your account. Right, still working with a couple of these examples. We've got People's Bank offers a 5.42% compounded continuously, there's the key, on CDs. What amount invested now would grow to $20,000 in 30 years? So compounded continuously tells us that we are using that A equals PE to the RT formula. This is going to be our rate, the 5.42, but again, we do have to change that to a decimal, not a percent. So we're going to go 1, 2. So our rate is going to be 0.0542. What amount is invested now would grow to, so we want to end with $20,000, so that's our A. And of course, 30 is our T. That's how long we are investing that money. So when they're asking us what amount is invested, they're asking us for P, the principal. What money did we put into this account to get $20,000 in 30 years? So let's see, 20,000 in for A. We don't know P, that's what we're trying to find. E raised to the 0.0542 times 30. Start solving for that P. I'm going to start out by multiplying 0.0542 times 30. And I got 1.626. Now we want that P by itself. We want that P by itself. So I want to get rid of the E that is raised to that 1.626. So it's P times that. So if I want to do the opposite and get rid of it, I'm going to divide both sides by E to the 1.626. And so that would cancel, leave me with just that P. And then I would be able to go to the calculator there and do 20,000 divided by E to the 1.626. And this gives me $3,934.30. Right. Looking at our next one, which is the last one we've got here for exponential. It says at what interest rate, so we're trying to figure out what is R, right? What interest rate to the nearest hundredth of percent would $16,000 grow to $20,000? So This looks like what we're starting with. This looks like what we're ending with. If it's invested for 5.25 years, so that's our T, and it says compounded monthly. Compounded monthly tells me that N is going to be equal to 12, and it also tells me that this is the formula that we are using for this problem. Right? We are using this formula. It does not say the word continuous, so we are not going to use that continuous formula. We are going to use just our compound interest formula. So let's plug all these values in. So 20,000 in for A, 16,000 for P, 1 plus, we don't know the rate, that's what we're trying to find. N is 12. Raised to the 12 times 5.25, because 5.25 is our years. Okay, and we're ultimately trying to solve this for R. So first thing I'm going to do is simplify that exponent. So 12 times 5.25 is 63. I'm going to divide by 16,000, because again, our goal here is to get that R by itself. So 20,000 divided by 16,000 is 1.25. Now this point we have 1.25 equals all this stuff here raised to the 63rd power. All right, so think about it. What if it had, instead of being 63, it had been a 2 or a 3? We would take the square root or the cube root to get that stuff inside the parentheses by itself. But since here it's a 63, we are going to take the 63rd root of each side. All right, and so we can go in our calculator and do that 63rd root. Right. I can't go to that screen, but I'll kind of tell you what you have to type in. So you have to go to type in 63, the number, then you go to the math button, and you go to the one, I believe it's number 5. It has an X and then a little radical symbol. So you'd select that one, and so on your screen it would make that an index at that point, and then you would type in 1.25 and hit enter. And so that, type in the index first, then go to math, and like I said, I believe it's number 5, right, that has the X with the radical symbol. You'd select that one, and it would allow you then to do the 63rd root of 1.25, and that comes out to be 1.0035482141. And then on this side we have 1 plus R over 12, right? Again, we're still trying to get that R by itself, so next I'm going to subtract that 1 from both sides. Right, notice how I'm not rounding until I get to my final answer. And then finally we want to get rid of that 12, so we're going to multiply. We're going to do 12 times 0.00354821, and we get 0.0426. And then if I change that to a percent, we're going to go 1, 2. So we're going to get 4.26%. That is our rate for us to be able to increase our money from $16,000 to $20,000 in 5.25 years. All right, so that finishes up for exponential functions, so just some basics of exponentials and then doing some word problems there. Now we're going to kind of look at logarithmics. All right, so logarithmic, we do these together because logarithmic is the inverse of an exponential and vice versa. Exponential is the inverse of a log function. So our basic log function is just f of x equals log base a of x. It says where a and x are positive real numbers. A is called the base, x is called the argument. And I mentioned this already, but I'll highlight it here. It says the logarithmic function is the inverse of an exponential function. So if you have something like log base 3 of x, right, that is the inverse of an exponential that is log base 3. So those two there are inverses of one another. A couple of properties of logs, all right. It's got log base a of a is equal to 1. Log base a of 1 is equal to 0. Log base a of a to the x is just x. So basically that's saying that the log base a and the exponential base a cancel each other out. Same thing is true if you have an exponential that's raised to the same log base. They'll cancel each other out, leaving you with just x. If you see where they just write log, so you see it right here, log, that is understood to be a base 10 log. So they may or may not write that 10 there. And then we have a natural log, which we write here. This is an L and an N. Right? Natural log is a log that has a base of e. So base e, which is your irrational number there, the one that was 2.72, etc. That and then natural log are inverses of one another. All right, so starting out with logs, we're going to look at a couple of properties of them, then we'll get into graphing one of them. It says use the calculator and or the properties listed above to find the values of the following logarithms. Round each answer to 4 decimal places if necessary. All right, so our first one here, all right, remember if we see just log with no base there, that's an understood base 10. So I'll kind of write it like that for this one, because then that allows us to use that property where it says if it's the exponential of the same base with a log, those cancel each other out, and it leaves us with just 3x plus 1. For example, B, that's one you just need to plug in your calculator. Just use the log button. Same thing for letter C, all right? For number 10, or excuse me, letter B, this again is a base 10, and that is what your calculator defaults to. When that log button you see there on the calculator, that is a default base 10, so you just need to plug that in. You do also have a natural log button on your calculator, so you can do that. The same thing for letter C. Now in this last one here, you have natural log of a base e. Remember we said natural log and base e are inverses of one another, so they're going to cancel each other out, leaving us with just a 2k. Right? And so for B and C, after you've typed those in the calculator, of course, you can go into Moodle and open up the answer key, and you can see if you got those two correct. Again, they're just typing those two in the calculator. It says when graphing, for some calculators, you will need the change of base formula. So depending on how updated your calculator software is, sometimes your calculator will allow you to do different bases besides just a base 10, but sometimes they do not. So you need a way to do that, to change something that is not a base of 10 to a base of 10. So that we do that through what we call the change of base theorem. Right, and so here you can basically see what it is. It is log base a of x is equal to log base b, which that b would be 10 of x divided by log base b of a. Right. Caution when evaluating a quotient like log of or natural log of 12 or natural log of 7. do not confuse that with natural log of 12/7. Those are different. So these two right here, these are not equal to one another. All right, so make sure you notice that natural log of 12 divided by natural log of 7 is different from natural log of 12/7. All right, so doing a couple of these, use change of base theorem to find the approximation rounded to 4 decimal places. All right, so we have log base 4 of 20. So based on the rule, all right, notice it says log of x divided by log of a. So log of x, 20 is in the same place as x, divided by log of a, 4 is in the same place as a. So we'd have log of 20 divided by log of 4. And again, you would just type that in your calculator. And we would get approximately 2.1610. Right, I'm probably going to end up just making a separate video that focuses just on the calculator. I'm afraid if I go to that calculator right now here, it might stop recording my video. So that's why I'm not going to that. All right, I'll do another one, letter B. Log of log of x, which is where 3 is located, divided by log of a, which is where pi is located. So this would be log of 3 divided by log of pi, and that comes out to be 9.597 approximately. All right, and I'll leave those other two for you to try on your own. I will say, again, like I said, I'm probably going to just make a separate video to kind of show you where some of those calculator buttons are located. When graphing logarithmic functions, you will need to find the vertical asymptote. So this again kind of proves the idea where exponentials and logs are inverses, because we said exponentials have horizontal asymptotes, logs are going to have vertical asymptotes. For most equations, the vertical asymptote will be x equals 0. It says unless you have a horizontal shift, so something that is added or subtracted to the argument of the function. So that would mean inside of those parentheses. Inside of those parentheses would be where you would see a horizontal shift happen, and that would change your vertical asymptote. As stated above, you may also need to change of base to be able to do a base other than base 10. All right, so first thing I see here is that indeed this one is going to have a vertical asymptote that is going to be different than just y or x equals 0, because it's got that x plus 2 there. So easiest way to figure those out is just take x plus 2, set it equal to 0, and solve. So we're going to get a vertical asymptote at x equals -2, and I will graph that. And kind of like we were doing for the exponentials, we're going to plug each of these x values in and then see what it gets, and we'll graph those. So log base 5, I'm going to plug in a -1. So this is going to be log base 5 of 1 plus 1. Which again, you might have to do log of 1 divided by log of 5 and then do plus 1. And you should see that that gives you 1. Next one, log base 5, when I plug in a 1, that's going to make that a 3. So log base 5 of 3 plus 1 is going to be 1.6826. Then we'll plug in a 3. 3 plus 2 is going to be 5. Plus 1 ends up being 2. Plug in an 8. 8 plus 2 is 10. So log base 5 of 10 plus 1 comes out to be 2.4307. So now we can plot those points. So -1, 1. -1, 1. Then we have 1 and 1.6, so a little over a half. 3 and 2, and then 8 and 2.43. And we're going to draw in our function. So you can see it gets really close to that vertical asymptote, but it doesn't actually cross it. For our domain, we're talking x values from left to right. So this one does not start until we get to around -2. And then that arrow is pointing to the right, meaning it's going towards infinity. The range, talking about those y values from bottom to top, it is pointing down, so it's going towards -infinity. And then as that function, it's going really slow, but it is continuing to increase there, so it's going towards infinity. Right, and then it asks if this is concave up or concave down. This is concave down because you can kind of see how it opens down. Right. And it is concave down for x values that go from -2 to infinity. All right, got a couple more problems here and we'll be finished up with this these two sections. It says because logarithmic and exponential functions are inverses of each other, logarithmic functions can be defined as the following. It says this is very helpful when we will learn how to solve both exponential and log equations. We will learn how to change forms when we solve these equations. All right, so a couple word problems here that involve some logs. It says the magnitude R on the Richter scale of an earthquake of intensity I is given by this equation, where I sub 0 is the intensity of a barely felt zero earthquake. The earthquake that destroyed San Francisco in 1906 was a 10 to the 8.3 times a intensity on the 0 level earthquake. What is the magnitude on the Richter scale? So magnitude is R. So we are trying to find R, right? And it says I is the intensity of a specific earthquake. So we know in this case, using this formula, we know that our earthquake in that San Francisco one had an intensity of 10 to the 8.3 on that Richter scale times the I sub 0, and then that would be over the I sub 0 because it says that it is 10 to the 8.3 times the intensity of a 0 level earthquake. Right, a 0 level earthquake we said was I sub 0. So that's how you can see there it's 10 to the 8.3 times the 0 level. Well, when I see that, I notice that I have an I sub 0 in the numerator and I have one in the denominator. So they're going to cancel, which is going to leave me with R is equal to log base 10 of 8.3. Well, if this is just log log, I know that that means that's a log base 10. So if I have a log base 10 of an exponential base 10, they're going to cancel out. So this is going to tell me that this has a magnitude of 8.3 on the Richter scale. 8.3 on the Richter scale. All right, and last one here. It says when the air temperature or the outside air temperature is anywhere from 72 degrees to 96 degrees Fahrenheit, the temperature in an enclosed vehicle climbs by 43 degrees in the first hour. The bar graph in the figure below shows the temperature throughout the hour. The function f of x equals 13.4 natural log of x minus 11.6 models the temperature increase of f of x in degrees Fahrenheit after x minutes. Use this function to find the temperature increase to the nearest degree after 50 minutes. How well does the function model the actual increase shown in the figure? All right, so they're telling us this is our function. And they want us to figure out the temperature increase to the nearest degree for 50 minutes, all right? And it says x is 50, right? Because it says after x minutes, so x is 50. So we're going to plug in 50 for x. And we could simply just start plugging some of this stuff in, do 13.4 natural log of 50 in our calculator. And that's what I got. And then we'll subtract 11.6. And we got 40.82, which if we round it to the nearest degree, that would be up to 41. And so then if I look at the chart here, at 50 minutes, so that's that blue bar that you see there, at 50 minutes, we see that it anticipated that it was actually 41 degrees, and that is what we got when we plugged in 50 in for x. So how well does it actually model the function? It models it very well, because we got exactly basically the same number for 50 when I plugged it into the equation as we did have in the graph there. All right, so that completes sections 3.1 and 3.2. Again, I'll post a separate video that kind of shows you where some of these buttons are on the calculator so that you can kind of go through and know where they are.